So last time we talked about fermions, electrons, and introduced this free electron gas or Sommerfeld gas in three-dimensional sphere. So you get a Fermi sphere, right? Okay, so you get the spherical shape of the Fermi surface, where at zero temperatures, all electrons are fully occupied inside this Fermi sphere and fully empty out of the Fermi surface. So that is the simplest case we can imagine that we can solve the Schrödinger equation more or less exactly with the three-dimensional electron gas without interaction. So we will use that picture later when we talk about the energy gap and also quasi-particles. So there's very important properties for fermions, which is related to the Pauli exclusion principle. Namely, if you consider two electrons and with Schrödinger wave functions, psi I and psi j, and here and there in space, and you want to exchange these two electrons, and therefore their wave function also get interchanged. But this there's a whole two electron system. When you do the exchange, we'll pick up the minus sign. Okay. So this property is called anti-commutation. So this is the characteristic of Fermi-Dirac statistics, that two fermions, when you interchange their wave functions, you'll get the overall minus sign when you exchange them, their wave functions. And we will derive such a property when we second quantize this electron operator. But this is a consequence of the Pauli exclusion principle. And that's why you get this Fermi-Dirac. Remember, this is your homework exercise. It's a +1. But once we have such a naive-looking Sommerfeld electron gas, we would like to add the periodic potential to this Fermi sphere. Remember, last time I used a kind of a cartoon picture, mimic this periodic potential of the underlying lattice that will confine these ions on the lattice and also confine the electrons surrounding those ions. Right? Okay. So but in this very naive picture of a free electron gas, there's no periodic potential here. So there's no lattice. So we need to put this lattice back and see how it gives us. So remember, if I make a plot of this energy versus momentum for a free electron, and I could fill up this states up to certain energy, which I call this Fermi energy, and this is called the Fermi energy. And the momentum corresponds to the Fermi energy is called the Fermi momentum, which the Fermi energy is the chemical potential, which is the energy required to actually add one more electrons in your system. Okay, so when your electrons are fully, say, occupied up to the Fermi level, and still not fully filled, because we have still many empty states available above the Fermi energy. In such a case, this is a metal, right? This is the metal. If we have partially filled so-called energy bands. But this energy band is just one here if we don't consider the periodic potential. But now let us just include this periodic potential. So you'll see that this band is going to split into different energy bands, and the possibility to show such band structures. And the electron band that contains the occupied states is called valence band. And then there's an energy gap between those different bands, and this gap is proportional to this periodic potential. And this is a very important consequence of this periodic potential in the homophoreal electron gas. And this type of band structure can be derived from the most general theorem called Bloch's theorem. This is also something that you should know. For example, if you look at Oshkar from Mermium, which is the very useful textbook for solid-state physics, in Oshkar Mermium, chapter 8, there's the statement about the Bloch theorem. So let me just write it down. Hamiltonian. So it says the eigenstate psi of a single electron Hamiltonian with this form in the presence of a periodic potential. Namely, the potential goes back to itself. If you simply just shift the position vector r by a lattice vector, capital R, this simply says that the periodic potential is periodic because it has the translational invariance that the strength of the potential remains the same upon lattice translation, right? So if you shift this position by integer multiple lattice vector, and this potential energy is still the same, okay? But under such a condition, for all lattice vector r on the Brovitz lattice, just some ordinary lattice, for example, the cubic lattice or whatever lattice in your solid-state textbook. So the eigenstates of such a system can be chosen to have the following form, where u n k r plus capital R is the same as u n of k of r. So, namely, the solutions for this single electron under periodic potential has this following periodic structure. Namely, there's a plane wave vector e to the I k dot r multiplied by a function which we call the u n k of r, where n is some quantum number and k is the wave vector of this plane wave. Okay, where this u and k satisfy this translational invariance. Okay, so this is something non-trivial because if you don't consider the periodic potential, your eigenstates of this free electron gas is nothing but plane waves, right? The plane wave. But once you impose this periodic potential on the single electron, the solution coming out of the Schrödinger equation has this periodic functional form multiply the plane wave. So it's not just a plane wave, but there's an additional factor multiply this plane wave, this additional factor satisfies this translational symmetry. So this is your homework. Prove it. So this is something that you should know. But I'm sure that most of you have not studied this, the Bloch theorem. You know the name, but you don't know what is this. It's time to figure it out by yourself. We will take advantage of such a Bloch theorem for later purposes when we argue that there's energy bands. So we just take this for granted here, and we could understand this band structure of a almost free electron gas, but subject to such a periodic potential. And this eigenstate shows this periodic form in addition to the plane wave. And under such circumstances, we derive this energy gap. So this is the important steps, and which is electron in a weak periodic potential. By the way, so the proof for the Bloch theorem can be found in many textbooks. Almost all solid-state textbooks should provide such a section where you could either use the translational operator to show this, or you can simply just solve the Schrödinger-like equation for this Hamiltonian. And either way, you could use the knowledge that we introduced last time, namely the reciprocal lattice vector and the lattice translational invariance, and you plug into the Schrödinger equation, and you could derive such term, un of k. So let us just assume that we know this Bloch's theorem, and we know this eigenstates of electrons in the presence of a periodic potential. So we could just take advantage of such theorem, and we can show that we can derive energy bands in solid-state system with electrons. So let us just sort of derive such a statement. The eigenstates or eigenfunctions following this Bloch theorem could be rewritten in terms of the following form. So you can show that this is e to the I k dot r multiplied by sum over reciprocal lattice vector g, a coefficient c k minus capital G, e to the I minus g dotted r. And you can very easily see that this is your u k of r. All right, so I already, show you part of the solutions that you should do in your homework. Okay, so the solution for such a problem is given by this combination. And what we call uk of r is nothing but the summation over reciprocal lattice vector capital G. And inside the summation, you get some coefficient attached to this wave vector, little k minus capital G, and times this Fourier factor of a reciprocal lattice vector G. But you still need to derive this form. But let us just take advantage of such a Bloch theorem, and we could plug into the Schrödinger equation, and you will get such kind of a coupled equation, linear equation. But you know that you have many different electrons, and suppose we just consider 2 electrons, which shows the energy bands with a parabola, and it is centered around, say, lattice vector, reciprocal lattice vector G prime, and also have another parabola of another electron states centered around different reciprocal lattice vector G. And for example, this is just electron number 1, and this is, say, electron number 2. Okay, so each single electron shows this parabola in their kinetic energy, right? This quadratic band, and this two kind of a dispersion of a free electron kinetic energy can actually have a meeting point or a crossing point somewhere in between, all right? But you can consider you get many so-called degenerate points, okay? But here we consider just simplest possible degeneracy, which is the 2 free electron levels which are degenerate. So degenerate states refers to the fact that 2 different quantum states have the same energy, called degeneracy, because this is the energy, and if this yellow curve meets with the red curve at a single point right here, and this point is called the degeneracy point, because at this point, either you look at the yellow band or the red curve, it has the same energy in both curves. So we call this 2 degenerate levels, or 2 degenerate plane wave solutions, so which represents this 2 almost free electron levels. So this is dispersion for 2 free electron, in the absence of this periodic potential imposed on these 2 free electrons. But now let us just do some calculations very close to the degeneracy point by including this periodic potential here. Okay, so let's look at how this U, I haven't told you this periodic potential. The form of periodic potential can be written in terms of this form. Again, it's sum over lattice, reciprocal lattice vector G e to the I G dot R. Okay, so you can very easily see that this U of R satisfies this translational invariance if you shift the R by some lattice vector G, and you get back to the U of R. So the U of R is a one possible form of a periodic potential. So let us just consider this 2 degeneracy, degenerate states right at the intersection between the yellow and red curves, and we include this periodic potential, and you'll see later that this degeneracy is going to split it, and there's an energy gap developed right at this intersection. So you'll see energy gap opening. All right, so let's take a short break. When we come back, let's just derive such energy gap by solving for the Schrödinger equation for almost free electrons subject to the periodic potential. So by the way, you could find all these derivations in this Kittel's first book, Introduction to Solid State, or Oshkar Fermion. So these equations can be found everywhere. Any questions so far?
想问一下，就是前面说波函数交换会做一个符号，实际上是波函数真的相交换，还是是operator的交换而已？
So both. You could define the electron operator in terms of the second quantized form, but the second quantized electron operator is directly related to the Schrödinger wave functions. So in a way, when you exchange two particles, you exchange the operators, and at the same time you exchange the wave functions. It's the same thing. But you don't know it's the same thing unless we define the second quantization. So you can look at this quantum particles in two ways. One is the Schrödinger wave function, another is the second quantized fields, operators, and they're intimately connected to each other. But we need to define those operators. So far, it's still based on the Schrödinger equations. I haven't really talked about second quantization, but it's just some background knowledge is required for all of you to get ready. Right? Some of you may be ready, but I suppose that many of you are not ready at this point because many of you have not learned those things that I reviewed. Is that right? So let's just look at these two degenerate points and look at the linear equations coming from the Schrödinger equation for such a system. And let me just write down this result equations. This is K prime, this is K. So this capital K and K prime is the same as G and G prime. Just to define my notation. And suppose we have two degenerate levels and representing two electron plane waves. And their momentum is centered at two different reciprocal lattice vector, K, capital K and K prime. But we can define this K and K prime this way. Suppose I label this to, say, reciprocal lattice vector G, capital G or capital K by K1, K2. Then we have two different situations, namely, if capital K is capital K1, K prime is K2. That's one possibility. And the second one is when you exchange this to reciprocal lattice vector. So if you consider the first case, capital K is actually capital K1 and capital K prime is capital K2, the first linear equation. And if you consider the second case where this capital K and K prime are interchanged, you get a second linear equations. Namely, for these two degenerate levels, you get two equations once you solve the Schrödinger equations for this, in the presence of periodic potential. So you could actually solve this equation pretty easily. You could define this little q and capital K, K2 minus K1. Suppose I define this momentum transfer little q, which is little k, subtract from this capital K1. And this capital K is defined as the difference between these two reciprocal lattice vector, capital K2 and capital K1. So then you could simplify this linear equations in this following form, and you could, to get the new, say, eigen energy epsilon, you could solve this by two determinants that's written here. Here, this epsilon 0 is the free electron kinetic energy, and this epsilon is the new eigen energy by including U. So epsilon 0 is the electron energy, kinetic energy of a free electron gas in the absence of the periodic potential, but this epsilon is the eigenenergy of the system, including this periodic potential. So you could derive this epsilon in terms of the epsilon 0 by demanding that this 2 by 2 determinant to vanish. So by the way, this u minus k is the same as u k star, where star is the complex conjugate of this potential. Okay, so let me just write down the determinant. So you will get the eigenvalue. So for those of you who are not familiar with this derivation, you could go back to the Kittel first book or Oshkar from Birmingham and look at this almost degenerate free electron eigenstates, but subject to the periodic potential. And so once you include this periodic potential, is nearly 2 free electrons, and you will get a solution that satisfies this coupled linear equations, and you'll get the corrected a new eigenenergy epsilon in terms of the free electron kinetic energy and the weak periodic potential. So this is the source of the energy band and energy gap, because you will see immediately that you open up the gap right at your zone boundary, 1/2 capital K. So remember previously, in the absence of the periodic potential, your projective bands is something like this. So you get the energy levels. Of course, you get another branch on the left-hand side. So that is your case before the periodic potential is imposed, so that you get a free electron kinetic energy without a gap. But once you impose the periodic potential there, you open up a gap right at your zone boundary, Brillouin zone boundary, where this little q equals 1/2 of capital K, where capital K is the reciprocal Lattice vector. So you can immediately see that when your little q is at 1/2 of capital K plus or minus, and your new eigenvalue is simply just this, your non-interacting kinetic energy of the electron, epsilon 0 of q plus or minus the magnitude of our periodic potential strength. And this is precisely the origin of your band gap right here. So this is 2 magnitude of u k. So you open up a gap right at this degeneracy point. So this is the point that you have this degeneracy. Okay, so before considering this periodic potential, just degenerate states. Okay, but this degeneracy is lifted by the periodic potential, and therefore, this single band is split into 2 bands, right? And there's an energy gap between these 2 bands is emerged. So now we form energy bands and a band gap between different energy bands. So you could populate this your electrons, almost fill up this lower energy band, and once you complete populating all these electrons states for the lower energy bands, then you should stop, because if you would like to populate one more electron in this fully occupied energy band, you need to pay the price, because there's energy gap. There's no states available inside this gap, completely empty. There's no states available. So you need to inject at least 2 times magnitude of the UK, that amount of energy, so that you could populate additional electrons above this lower band or in the upper band. So the first states that you could populate in the say upper band is that you inject the energy 2 times U of k above this energy level that's at the top of your lower band. Okay, so in such a case, if your electrons fully occupy the lower band, the system becomes an insulator, because you will need to actually inject additional energy to make electron populating in this so-called excited states, or the upper band, so that electrons at the upper band could actually get excited very easily by thermal excitation and so on. But if you have only half-filled energy levels in the lower band or partially filled, then you get a metal, because you could always excite the electron states within the lower band without costing any extra energy, because those states are so close that just a tiny little bit amount of thermal fluctuations will be sufficient to get electrons to the states that is slightly higher. For example, if you would like to excite this electron to one floor above this energy level, and that is almost costing nothing. And if you have such a situation, your system is in a metallic state. So you could distinguish metal from the insulator, but the requirements that you need to derive the energy gap. And in order to have this energy gap, we need to consider this periodic potentials imposing to this almost free electron gas. So that is the, the prerequisite knowledge that everyone should be familiar with. Namely, you know how to get energy bands, you know where this band gap is coming from, and what is the effect of the periodic potential on the almost free electron gas. This is just a review, okay? So everybody should know. So then you could derive this wave functions at this two different energy bands. For example, the wave function or the eigenfunction, the magnitude square, is actually cosine over 2 dot r square for the positive branch, and you get a sine function at the lower band. So just very close to this zone boundary or this degeneracy point, if you are slightly above this degeneracy point where you reach this minima energy of a upper band, and the eigenfunctions is proportional to this cosine function. However, if you are slightly below this degeneracy point, you get the lower branch, and the eigenfunctions follow the sine wave function. So this is epsilon minus, and this is epsilon plus. So far, it's just some introduction or review of your solid state 1. So I guess that's all about this fermion system. We will introduce a new concept called the elementary excitations or quasi-particles, as I already told you. But before that, let's just review the bosonic part. So far, it's about fermions or electrons. So let's talk about the bosons. So again, the bosons satisfy this Bose-Einstein statistics, namely, if you interchange two bosonic wave functions in your two boson system, then you don't get the minus sign, namely, so it's the same as before. So it satisfies this Bose statistics where the MB shows this Bose factor where there's a minus 1 in the denominator between 1 and this exponential factor. Good. So what is the simplest example of the bosons? You should know that already, because in quantum mechanics you already learned how to solve these eigenstates and eigenfunctions of a simple harmonic oscillator. So again, everybody should know this. If you have this harmonic oscillator which shows this quadratic parabola for the potential energy, and such a system could be solved pretty much easily. Two approaches. One is by brute force way, that you solve the Schrödinger equation subject to this quadratic potentials, but there's a smarter way, which is in spirit the same as introducing the second quantized fields, and this is the approach that I should remind you. So time is up, but we will continue, reviewing this quantum mechanics for a simple harmonic oscillator. And as I mentioned, when you consider the coupled harmonic oscillator on the lattice, and this is precisely the phonon, or lattice vibration is nothing but the collection of coupled simple harmonic oscillator. And we will understand how this phonon comes about when we review the simple harmonic oscillator for a single quantum particle, and then we can generalize this to, say, many harmonic oscillators, and they are coupled together, and to mimic this lattice vibrations in a realistic lattice. So that's all for today, and so let me summarize. So you should refresh your memory about this Bloch theorem of an electron system, and convince yourself that there's indeed energy gap emerges if you include this periodic potential to this nearly free electrons, and refresh your memory on this single harmonic oscillator, and which we will review on Wednesday. Okay, so once we go over this basics, and we should move forward to introduce the more advanced concepts such as elementary excitations and quasi-particles and electron-hole pairs and so on and so forth. If you have questions, you can stay and let me know. If not, I'll see you on Wednesday.